accept. So this one? Yeah. Okay. Nice. So I did my undergrad here at the physics department. And I spent 5 years in US doing my PhD at Embry-Riddle Aeronautical University. Then I did a postdoc in Florida, University of Florida. And all that time I was working on gravitational waves in LIGO. And currently I got the position at as an assistant professor here at the department. Also I got a Polish return grant, which I'm so grateful and so excited to start my new journey right here. So first I will talk about generally about gravitational wave astrophysics, about the gravitational wave sources, about the gravitational wave detectors, and then I will talk specifically about gravitational wave.
Przepraszam, znowu nie słychać. We still don't hear.
Maybe it's like running out. Okay, how about now?
Yes, now it's okay.
Okay. Perfect. Okay. Okay, so at the beginning, I will talk about the gravitational wave astrophysics in general. Then I will talk about gravitational wave searches, model independent searches, specifically the fourth observing run that is currently going on, whatever is publicly available. And then the direction of searching for so-called higher harmonics. And then I will summarize my talk. So gravitational wave astrophysics. First of all, a very quick recap on what is the dynamic universe, how to generate gravitational waves. And for that, we need a quadrupolar emission of gravitational waves. Simply, if you think about objects, moving objects, if you have something ideally spherically rotating, it does not emit any gravitational waves, you need to have some sort of break in the symmetry. So if you have a mountain on the rotating, for example, pulsar, then it is emitting gravitational waves. If you have two compact objects, they also deviate from spherical symmetry. So it's also, it's actually the most efficient source of gravitational waves. If you have exploding star, you have a lot of different asymmetries, a lot of different resonances that deviate from spherical symmetry, and it also generates gravitational waves. And in a very loose terms, we can define divide the gravitational wave sources. Okay, battery is dead here. Gravitational wave sources into we can call it vanilla sources, like stellar mass black holes, like black holes with just circular orbit. So this is what we observe a lot, and it's a source that we call inside like vanilla gravitational wave, vanilla binary, and then the whole range of exceptional gravitational wave sources. So what do I mean in terms of exceptional gravitational wave sources? So we want to look at these exceptional gravitational wave sources because they may play the key role in exploring the universe and understand physics, fundamental physics on a more fundamental level. So we can have new gravitational wave source populations. For example, we have we detect a lot stellar mass binary black holes, but we haven't detected yet a good binary with eccentric orbits. We don't have yet detection of a system of a hyperbolic encounter when you have like more static black hole and a flyby another black hole. We don't have we haven't detected yet head-on collision. We don't have yet detection of binaries with of black holes with subsolar masses or like any objects with subsolar masses. We don't have extreme mass ratio binaries yet. So this is for the binaries. And then for any other source like core collapse supernova, neutron star, pulsar glitching, cosmic strings, all of those are also waiting for the discovery. And this will be our exceptional gravitational wave sources. We can also have, we want to also detect more and more multi-messenger sources. So we already detected light from the binary neutron stars back in 2017. We also detected neutron star black hole, but we haven't detected yet light. And also we haven't detected yet the post-merger phase of a binary neutron star. Then sources that have interesting properties. So if we have stellar mass black holes, but with some unusual properties, we can also put it in the basket of exceptional. And then we can have within general relativity, those that have pre-merger and post-merger higher harmonics content. And I will talk about that at the end of the talk. Gravitational wave second polarization component. So far, we detected only one polarization component. So the second one is still waiting to be discovered. The black hole kicks, the gravitational wave memory from like a variety of sources. Effects of precession is still not yet found. We haven't detected very high spins of binary black holes. We haven't seen yet the black hole formation, and so on. And then beyond general relativity, there's a large library of different possible scenarios, like gravitational wave echo when you have two compact objects, and then gravitational waves basically bouncing between both of them. Objects that are not black holes, but like some other exotic compact objects. And so theories beyond quadrupolar gravitational wave polarization. So, yes.
So many sources. Can you really distinguish between the sources just by observing gravitational wave? This must be difficult.
It's very, very difficult. And yeah, this is the whole range, but yeah, people are focusing on, say, the most promising source at the time. So we have, there's a lot of infrastructure for stellar mass binaries, but a big development is towards detecting an eccentric, a binary with eccentric orbits. There's some work on hyperbolic encounters, head-on collisions. There's actually a lot of work for finding binaries with the subsolar masses. There's plenty of work toward like core collapse supernova. So yeah, like people try to pick up source that is the most promising at the time. It's a long way. I can even say about the intermediate mass black holes that were discovered a few years ago. When it was discovered, the models were not yet fully developed, and it also costed a lot of work during the detection. So yeah, it's a challenging problem, I would say, to first detect it and then make sure that what we observe is actually the source that this exactly source. Yeah.
Very careful and not observed during the context of QR.
Which one?
Echo.
From it might be like a blurry area. Like I'm not an expert in gravitational wave echo. I've heard it in the context of going beyond GR when you have some exotic matter, but yeah, I'm not. I cannot fully answer. I put it here because usually people refer to it not within like standard GR. Okay, so a quick recap about gravitational wave detectors. When a gravitational wave is passing between two objects, it causes a difference in length between these two objects of a value delta L. And what we measure is basically the strain. So delta L over L. So the longer detectors, the more sensitive they are. And in reality, we are using gravitational waves interferometers. So it works that we have a laser source. I wish I have laser source. It's not working, but the battery is almost dead. Okay, so we have but we have something more classical. So we have a laser source, and then the laser source is split into two beams going to one arm. The second arm is reflecting at the end and mirrors, goes back to the beam splitter, and then recombines in the photodetector. And the whole detector is configured as a to have basically darkness in this photodetector because it's easier to find a little bit of light when it's dark than to detect a little bit of light when in a room that is bright. So it is called also a dark port. And then what this delta L means is basically the difference between the lengths of these two arms. So this is like the basic, the foundation of gravitational wave interferometry. And these detectors are very, very sensitive. And we need to have them like placed far away from any human activities. So this is an example of a detector that is in Hanford, which is on a desert of Washington State. And here it is me. I like to show it. I work on data analysis, but I also worked directly with the hardware. And before the previous observing run, I was actually inside the chambers of the detector, where you can see the mirror that is basically on like at the end stations. So this is how it looks. It's basically like 30, 40 centimeter mirror, super sensitive. So you have to be super careful when you do experiments inside. So at the moment, we have a network of 3 detectors that are operating: Hanford, Livingstone, and then Virgo. LIGO, Hanford, and Livingstone, they have the largest sensitivity. They're running between 140, 180 megaparsec, and they're observing at this very time. Also, Virgo is sensitive up to like 50 megaparsecs. So in a moment, I will actually show the timeline with more details. We have a KAGRA detector that was basically struck by the earthquake a few months ago. And at the moment, it's not observing. I was in Taiwan and I was talking to experimentalists, and they say like, yeah, when they go to the chambers, assess all the damage, they say like, yeah, there's some places where you can see that mirror basically hit the surroundings. So it's not, yeah, it was pretty bad damage. And the detector is underground, which was supposed to have all these problems. Yeah, to avoid, it went underground to avoid any of this seismic problem, but because the earthquake was was really strong and very nearby the site, around like 100 kilometers. Then the waves basically propagated not only on the surface of the mountain where the detector is placed, but also penetrated the mountain itself. So it's actually, they told that the whole mountain was actually moved for like 3 centimeters in one direction. So it was pretty bad. And this, unfortunately, and yeah, and Japan has this problem. But we also learning a lot about technology. Like people said that like one of other advantage of going inside the mountain was to say that you have a stable temperature. But what happened in practice is that you have all the electronics inside the inside that are basically hitting the surrounding and like at different rates. So they both have heaters and air conditioning to actually put the temperature stable. So it's yeah, with every technology we are learning new things, practical things. And then we have LIGO India, so detector that is currently under construction, and hopefully it will operate before the end of the decade. And yeah, at the beginning, it will be operating at the initial LIGO sensitivity. The hardware is already prepared to be shipped to India. So hopefully we'll have that before the end of the decade. And then geodetector that is in Germany, a small detector for testing the ground. And another one that is currently planned that I would like to mention is the Australian detector that will be devoted to high frequency. So a big scientific case is to find the oscillation of the final when we have binary neutron star merger, to see the oscillation of that compact object that happened during the collision. So this will be the main focus. And the high frequency means around like maybe 2-3 kilohertz. So this is way beyond from what we have at the moment. So hopefully it will get funded and it will be built. And the observing timeline. So we had 1, 2, 3, 4 observing runs. During the first observing run, our exceptional source was binary black holes. During the second observing run, the most exceptional source was binary neutron stars. During O3, the most exciting exceptional source was intermediate mass black hole. And during the O4, we have around we have 100 public alerts. So I can only talk about what is public, unfortunately. And LIGO was operating at around like 160, and it reached even 180 megaparsecs. Virgo had very serious hardware problem when you have to basically replace the mirrors, so it's very invasive situation. But they were able to solve all the problems, and they are running at around like 50-55 megaparsecs, and pretty continuously, which is so great for localizing the sources. And then KAGRA was hit by the earthquake, but hopefully they will be able to join the observing run at the end of O4. And then all the plans for O5 is the future. Okay, so let me talk about gravitational wave searchers. So we can divide them into basically 2 types: the model independent and the model independent, so-called burst. And model independent rely on templates calculated from general relativity. When we have binary black holes, binary neutron stars, maybe subsolar mass black holes, stuff that we can accurately model. And then model independent, it's basically anything from core collapse supernova, regular binaries, eccentric binaries, and all other exceptional gravitational wave sources. And then for the low latency, we have low latency analysis, so rapid identification of the sources in order to send it to the astronomical community for the follow-up. And then offline, when we collect the data, we understand the noise of the sources and we assess like proper significance to the detections. And for the model dependent searches, this is also called match filtering. We are cross-correlating our templates with the data. And these templates are derived from general relativity. And in order to do match filtering, you need to have an accurate representation of the signal. So you need very accurate models. And if you miss, if your model is not accurate enough, or you are missing the parameter space, you will lose the signal. This is what happened during the first gravitational wave detection when people didn't see, many people assumed that, oh, we see compact binaries only up to 15 solar masses. It happened that, yeah, the black holes that we detected had around like 30 solar masses. So the match filtering missed it, but the model independent searches, the burst searches detected it. So this is an example when you can if you don't properly assess parameter space or the model, then you can miss gravitational wave. Plus, all this match filtering assumes basically Gaussianity of the data, which is not true if we have a real gravitational wave detector. So it also plays a role. Now, the model independent searches and the main algorithm is coherent wave burst. This is algorithm designed for the widest possible sources of gravitational waves, and it doesn't assume any knowledge about the source. It can use some minimal assumptions. So for the compact binaries, basically anything with a chirp structure is our gravitational wave candidate. So it doesn't matter if we model it accurately, not accurately, if we have parameter space or not. Whatever is the chirping structure, this is our gravitational wave candidate. And such approach is very elastic, and it's complementing the match filtering search. And as I said, the very first gravitational wave was detected by these burst searches. It's not sensitive to the model. And then an intermediate mass black hole was also detected by this pipeline. And at that time, basically the models having very high masses of binaries were not yet like fully developed. So it took a lot of work to actually make sure that what we see is really our gravitational wave from intermediate mass black holes. And then it detects all other gravitational waves together with this template-based searches. And at the moment, it's the most sensitive algorithm in O4. Basically, not, practically no. Like you take the signal, maybe I can show it in a moment. And whatever is above the average noise, this is your candidate. So it doesn't matter where it can be coming from. It can be anything. Whatever it stands above the noise, this is our trigger. That's right. That's right. So yeah, we don't depend on anything of that. Okay, and the way how it works is basically you take the strain data, you decompose it in the time frequency maps. So this is just a sketch of 3 detectors. Then you add it all together, and then if you basically add data from each detector, then the noise adds incoherently, but the signal magnifies. So this way you can magnify the signal and find it more significant. So then you have basically such image. You do all sorts of statistics inside, and then you can transform back to the time domain, to frequency domain, and do all the further analysis. And this is an example of the first gravitational waves. This is basically how it looks. You have basically pixels in time frequency domain that create your event. So this is actually a good moment. Yeah, before talking about the searches directly, it's very challenging to create time frequency maps that are that accurately represent your signal. Plus, you have to represent properly the noise. So there's a lot of flexibility, but depending on the transform you use, you can have leakage in time domain, leakage in frequency domain. So basically, the energy can be like spreading all around. And this is an example of a previous transform that we're using, where you have a lot of noise basically spreading away from the event. Recently, we had developed so-called wave scan, when we can represent signal way more accurately and remove all these artifacts. So it's something challenging, and with time we are developing more and more accurate representation of the data in time frequency domain. And then how we search, we have the whole spectrum of searches. So we can, on one side, we have search for compact binaries, which we call them minimally modeled. And on the other spectrum, we have the most generic searches, which are like unmodeled. We can call them unmodeled. And here we can assume that compact binaries go up to around like 300 Hertz. And they have chirp mass, and we can assume some sort of procedure to take into account the populations and the model, but we don't use any templates. Just to clarify, then we have when a compact binary does not have keeping structure, for example, compact binaries from very, very heavy black holes. They are at a very low frequency. So the intermediate mass black hole, this is the intermediate mass black hole. It's around like 50, 60 Hertz. So in this region, we have a low frequency wall. So basically ground motion that basically prevents any detection. And then the merger is also like limited to lower frequencies. So we also can assume that it's we can make like certain small assumptions. And then on other spectrum, we have sources that we do not know how they look, or yeah, we haven't detected yet. Just we want to be as open as possible. So core collapse supernova is one example when the peak frequency is around 1 kilohertz with respect to the binaries that go up to just 300 Hertz. And then any shape of the signal that we detect is our gravitational wave candidate or our gravitational wave. And then we can have all sorts of sources that are in this category. Yeah, we are not as sensitive as for the compact binaries, but we are sensitive to anything that can produce gravitational waves. And then we have our low latency searches for the multi-messenger observations. And then searches for the new phenomena that I will talk about higher harmonics at the end. And let me give you an overview of the current observing run. It started last year in April, and then it will run until around like February, so it's a total of 20 months. But there is a discussion now about extending that for a few months, or at least I think even for until like October, November. So that would be exciting. The binding intrastar range, as I said, goes up to 180 megaparsecs, almost 60 megaparsecs for Virgo. A duty cycle is also pretty good. So this is the time when the detector was operating continuously. And then, yeah, I also include links for people to actually look at all the up-to-date information. And this presentation will be available also online. So the links will be available. And then KAGRA is our poor detector that was hit by the earthquake. But if they manage, they try hard, they will try to join all four at the very end. And this extra few months will give them a little bit more buffer to actually join the observations. And then current observing run, it is ongoing. This is the sketch of the sensitivity from a few days ago. So you can see that Virgo is around like 55 megaparsecs. Virgo, we're operating around like 140, 160. Livingstone detector tries to reach 180. And then the whole spectrum where you can see across the frequency range, the sweet spot is around like 100 to 300 hertz. This is where we find our compact binaries. And this is also from publicly available from a few days ago. And then we observed so far 105 gravitational waves, 81 of them in the O4A, in the first part of the observing run, and then 24 in O4B so far. And so this is roughly 3 detections per week. Almost all of them are compact binaries, binary black holes, and then there's 9 of them that have a probability to be not binary black hole. And then we have our match filtering, our pipelines. We have gravitational wave burst searches. So this is the most generic search for any sorts of gravitational waves, and then specific one for compact binaries. And also, quick mention that when we had a public alert from last year, it happened to be a special event with very, very light compact binaries. So it's something exciting. Like, we analyze the data, and we hope we can update people soon. And a special slide on the CWB so-called BBH search. So the search towards finding compact binaries. So it is tuned to find stellar mass, intermediate mass black holes, and it detects binary black holes regularly with a rate of around 80% together with match filtering. So it's pretty good. It's complementing match filtering, and it is capable to detect special, like exceptional gravitational wave sources. So whenever the model doesn't represent a certain signal, this is the most probable search that will pick it up, like the first gravitational waves or the intermediate mass black hole. And then so far we had only 3 public alerts, but they are not significant. So it's nothing interesting to talk about. For the public alerts, we have, you can expect getting the sky localization, distance, and source classification for the binary black hole detection. And then if we have any other detection from a burst source, then we'll have something related to gravitational wave energy or luminosity, the peak frequency of the signal, and the duration. And so far, we had only one public alert as that was like fairly significant, but then it was classified as noise. And during this run, we haven't found anything significant.
That's the messenger. I mean, that were identified as messenger events.
Not to what I know. I've heard about some weak correlation, but nothing strong yet. In OFO run, yeah. So yeah, and it's something also difficult when we have the binary neutron star detection. It was something surprising. The binary was so close, and we were lucky actually to detect light. And people predict that we might not see anything similar even till the end of the advanced detectors. So it's yeah, with that event, with the binary neutron star event, like we were lucky. But astronomers are following up like every hour event. So the last topic of the day is the higher harmonics. This is something that I'm getting slowly into. And if you have gravitational wave signal, you can, it's basically a sum of harmonics that are like numbered with L and M. And then the 2-2 mode is the dominant signal. And then higher harmonics, 3-3, 4-4, all other with higher L and M. These are much weaker, but they carry very detailed information about the source. So they're perfect for understanding like the orientation, for astrophysicists to understand what is the formation channel. So the generation of this higher harmonic depends primarily on the mass ratio of the binary. So if we have something like 1-4, 1-10 solar masses, then we have pretty strong generation of these higher harmonics. Spins, so whether the binaries are rotating the same direction or in the opposite, the precession, the eccentricity of the orbit plays a large role, or it's also inclination or angle of the system. So far, we have detected the so-called 3-3 mode, so the first higher harmonic, with these two events from O3. And then when we start having stronger gravitational waves with higher signal to noise ratio, then we start seeing more and more of these higher harmonics, and we'll be able to study gravitational wave sources way more precisely. And we will have to be able to study the history of the binaries and make more and more constraints on the gravitational wave theory, on different theories. So the case of these two events. So if you we did our work on also using our model independent searches when we also detected we assigned significance to these 3-3 modes. And the idea here is overall the math behind higher harmonics is complicated, but here we do use a very you can use a pretty much very simplified approach when the frequency evolution of the higher harmonics is basically proportional to your dominant 2-2 mode. And for these two events, we had mass ratio of around like 0.28 or like 1 to 10. This is like a 0.28, and this is a 1 to 10. So,
definition of mass ratio.
oh, it's like a mass of the binary of the first component divided by the mass ratio of the second component. So here, I think it was 3 solar masses, the lighter, and then 30 solar masses, the heavier binary. So this is basically M1 divided by M2. Other searches also found, and we also found a strong evidence of the higher harmonics. So in this analysis, basically we have our 2-2 mode that is where we have the signal and some noise, and then track of this higher mode that is basically like a little bit higher in frequency. So if we basically extract it, we can still have a significant the signal that is pretty strong. So there is a very strong evidence that these binaries have higher harmonics. And then finally, this is our development work. I have 2 students from the US, Chance Jackson and Kia Schulterman, and they are working on creating infrastructure for us to detect higher harmonics much faster, like as quickly as possible. It's for our model independent searches. So basically trying to estimate the mass ratio. And here we have an example of a binary of a mass with a mass ratio of 1. So these 2 masses are equal. And then when we have 1 to 10 compact binaries, and then we have you can see our track of the 2-2 mode, and then 3-3 mode that starts becoming visible. So this is what they are working on, and if we can quickly identify such events, then we can make a very quickly assessment whether we should work on them or not. It's both for the basically testing the theories, and also for the astronomers and astrophysicists to study these sources. So this is something that they are working on this summer. And as a summary, the gravitational wave astrophysics is an exciting field, and we have plenty of examples of exceptional gravitational wave sources that we want to discover, and they will most likely play the key role with exploring the universe. For the gravitational wave searches, I talked about the model independent searches, and they are suitable, and they already showed that they can make discoveries. And this is what I was working for the last 10 years. We have around 100 gravitational wave signals during this observing run, and the detectors are taking data continuously. And for the higher harmonics, they are perfect phenomena to study the sources in details and testing the theories. So thank you very much.
Thank you very much. And explaining this field class, such exciting fields. Now, guys, some questions.
I have a question. So can you make some conclusions about the universe, that our universe consists mostly of exceptional sources?
I would say at this moment, we detect just the, say, vanilla, but somehow exceptional like when we start seeing some certain source, it will be something normal. So yeah, this is just a term that we use for finding new things. So yeah, at the moment it's basically full of these exceptional events, but once we detect them, there will be sort of like something normal. If we detected gravitational waves from core collapse supernova, that would be almost yeah. If we detect it, if we have a supernova in our galaxy and we detect the gravitational waves, then that would be like super. It would be like a gold event. But yeah, maybe in the future it will be something like a regular. We'll see them like regularly. But yeah, like here we try to focus on those sources that carry some like unique information, or these are like new sources, rather than just regular like stellar mass binaries. Like stellar mass binary was exceptional at the beginning during the first observing run, and like each event, you know, 1 or 2 was exceptional, I would say. But then during O3, when we had them like once a week or twice a week, then it was actually interesting when people started calling them like vanilla, like normal gravitational wave sources, like no, we don't bother anymore. Oh,
there are some questions from.
okay, sweet. I don't know how it works, but yeah, maybe Srikat, you can unmute.
Yeah. Hello. Hi, Marek. It was a nice and interesting talk. And what I'm thinking is these methods might be very useful for the search of lensed gravitational waves, particularly in the wave optics regime where there is a distinct frequency evolution. So, are you aware of any such works where this method has been used for lensed gravitational waves? Maybe Hoto or someone using it?
Yes, that's a good question. So yeah, lensed gravitational waves maybe can be also placed in these exceptional sources. At the moment, we don't have model independent searches with coherent Webers because like on per person power, it's just something, yeah, it's like another interesting thing to add. There are a lot of searches in terms of the mass filtering. There are like pipelines. There are plenty of people actually who work on that. And from what I know, I was talking, the astrophysical prediction is that we should have within 1,000 detection, we should have one strong lensing candidate. And yeah, if we have now 100 plus 100, so before 04, we'll have like 300 events. With 05, we might have like several hundred, so we can start approaching, say, this 1,000. We start getting like a bigger chance to find this lens signal. So yeah, this is actually a very good point. I completely forgot about it. Yeah, lens gravitational wave signal is something that people are looking at, which could be detectable in like fairly near future.
Yeah, thank you.
Are
Okay.
there any more questions?
I see Mikołaj.
Yes.
Hello. Thanks again for a very nice talk. I enjoyed quite a bit. I have a question regarding some kinds of exceptional sources, namely head-on collisions and hyperbolic encounters. I'm not an expert here. Is there really any hope to see them with current ground-based detectors? Because it seems to me that they will not have any kind of periodic structure you could rely on when performing the data analysis. Is it correct?
Yeah, this is correct. They don't have, to make it even harder, they're kind of like similar to one of the worst glitches we have in the detector. So it makes it even harder. But yeah, like they're There are models, but they are like still like not anything close to what we can do with the match filtering. Yeah, for the model dependent searches, yeah, that's a big issue. But if we have model independent searches, if the signal is strong enough, so like SNR of 50, then it's a gravitational wave, basically for sure, without like many big assumptions. So yes, if we have a head-on collision or hyperbolic encounter, then yeah, model independent searches will be able to pick it up if the signal is sufficiently strong.
So you can only rely simply on assumption that the strain is big enough that nothing else explains that. I see. Okay, and regarding once again the strong lensed gravitational waves, I guess the biggest signature would be if you see the same event twice or 3 times because of time delay, multiple imaging. Is it correct?
Yeah, that's my understanding, that you have like two like alike images that basically represent the same source, and this is like basically the foundation. Yeah, but I'm not working directly with the in the lensing, but yeah, it's actually something exciting that we might be able to detect before the end of advanced detectors.
Thank you.
No more. No, yeah, I know. I just want to mention that there are no more questions from our online viewers. So yeah, please.
Why don't you take that we have run out of cooperation?
So we have gravitational wave plus and two copolarization components, and then if in order to detect them, you need to have the network that is sensitive to both polarizations. But if you the LIGO detectors the two LIGO detectors were built in a purpose to actually discover gravitational waves. So if you look at the map and you look at the arms, the arms are pretty parallel. So they can detect only one gravitational wave component. You need another detector that is like rotated 45 degrees for the second polarization. And Virgo detector is kind of like rotated, but in a practical terms, it's not. It's still not enough. Like this location is not enough to actually find this second polarization efficiently. Depending on where the source is on the sky, like the orientation of the source, basically the whole network is not really sensitive to the second polarization component. If we have KAGRA detector, that's a different story. Its orientation is actually allows to detect second gravitational wave polarization more efficiently. But at the moment, yeah, these two LIGO detectors plus Virgo are not fully capable to find the second polarization. So you have a certain degree of freedom of defining what is plus and cross, and usually if you go through the equation, you can basically rotate the polarization in such a way to align with the strongest. So basically, the strongest signal is basically your plus polarization, and the weaker signal is the cross. So it's so because of that, yeah, the second polarization is not really is always weaker. So you have like the dominant, but then you don't have the weaker component that we call cross. Oh, Einstein telescope. Well, that's if we have Einstein telescope in a triangular configuration, then yeah, it's sensitive to both polarization like equally. But yeah, now there are actually discussions, but that's actually the whole another story. Yeah, at the moment, the proposal is still to have like triangular shape to to alone detect both polarizations, but there is more and more discussions toward having two L-shaped detectors, and the orientation is unclear. It will depend on a lot on the funding and the locations. So yeah, we don't know exactly what will happen with Einstein telescope. Yeah, but yeah, the 3G detectors, the whole network, should be capable nicely to detect polarization, like both polarization and basically study the source in details. And but by the time we will have like a lot of higher harmonics detected and hopefully another sources. So yeah, like the next generation detectors is the whole dream of the future that will happen in like 20, 30 years, I would say.
Gravitational waves.
Which one?
Be extended like
Oh, yeah, that's like another. So yeah, people are looking for the. Oh, you mean like primordial, like a B mode, like the CMB polarization? No, this one are not, no, because the primordial gravitational waves are in the like nanohertz regime. Is like very, very low frequency, and these detectors are in between say like 20 hertz up to like 2 kilohertz. And LISA is around like millihertz regime. So you have LIGO, you have LISA, the space-based detector, and then you have the BICEP experiments. So it's in the most furthest frequency range. So yeah, like we can maybe do some. I haven't seen any actually studies towards understanding the primordial gravitational waves. Maybe there is some case, but detecting gravitational waves is basically no.
Oh, there is
okay, nice.
Okay, yeah.
Okay. You can unmute your mic. Yeah, Bogdan. Yes.
Yes, thank you. Thank you very much for nice report. I would like to ask you, what is the source of observed glitches? Such glitches is very similar to the signal from cosmic string. Thank you.
Okay, that's also very good question. So we don't know. The answer is we don't know. Like people looked at every piece of the detector. They studied for years, and we still don't know where it's coming from. It's basically very sharp and strong glitches. People think that they are happening. There are like charges on the mirror in itself, and like from time to time you have like a discharge, creating like a glitch signal, basically on the mirror that creates these glitches. So this is the region of the detector that cannot be properly studied because it directly affects the measurements. So at the moment, we don't know where these glitches, so-called blip glitches, are coming from, but the most likely scenario is in the detector on the mirrors where we cannot like directly study them. So yeah, like we wish to know, but it's something yet not discovered.
Thank you.
Okay.
So no raise hand. No raise. Yeah. So I think we can close.
Okay, thank you very much.
And then hold on, the last sentence. And I'd like to invite all of you.